lecture, I got through to the example where it talks about quadratic regression. That was a second example of something which is going to fit into our general framework for a linear model. So we had two examples of things that were going to fit into our general framework yesterday. So the quadratic regression was the second one, and the first one was what we call multiple regression. So multiple regression, we have our variables that we have to each observation, so are potentially explanatory variables, and then one response variable. So in this notation, the explanatory variables potentially are x, the observation I are xi1, xi2, up to xir. The observed response is then yi, and in our model we have a linear feature. We have a linear combination of the potential explanatory variables, the x's. Each one of them is multiplied by beta for that variable. So xi1 is multiplied by beta 1. And we also have the constant term, beta 0. And importantly, on the end, we have what we call, as I said yesterday, not always wanting to call it the error term, but the random part of the model, which is the epsilon r. Okay, so yesterday I said we could think of this as being in two parts. We have the linear predictor, which is all the bits with the betas in them, all the terms except the epsilon I, and then the epsilon I is the random part. So that's one thing that we can think of in this way, the quadratic regression, where yi is beta 0 plus beta 1 times xi, then plus beta 2 times a quadratic term, xi squared, and again then plus the random term, epsilon I. So here, the linear predictor, in inverted commas, is actually now a quadratic, and so this is giving the idea that the curve that you now might fit to your points would be a quadratic. Okay? As I said yesterday, in fact, the framework of the linear model we're going to describe, this is still included, even though you might think that because it's quadratic, it's not linear. Linear here refers to the behaviour of the beta terms, and it is linear in the beta terms. Okay, so I'm now going to move to a bit more of a clarification of that, and an introduction of some matrix notation. The matrix notation fits in well to the fact that we're dealing with things which are linear. Okay, so one thing that we can do, we can certainly do this, if we have n observations, we can put the n values of the response in a vector. This is going to be the standard column vector, like that. So y is just a column vector whose entries are the individual response terms, so the responses for each observation. Okay, so in the notes for the slides, we'll often write it as the transpose of a row vector, so you can see there it's been written as a transpose of a row vector on the slide. That's really simply a space-saving convention. It takes less room to write the transfer of a row vector than it does to write a column vector. But this is the column vector form is what's going to fit in with the way we're going to think of it. Okay, so we can do the same thing if we go into just back to the simple linear regression. So the case of this, where you just have r equals 1, so you just have one term there. You can put the x's for that variable into a column vector as well. So you could also have an x vector, which looks like that. And then if we think about our random terms, our epsilons, we can have a vector for them as well. Okay, so for each of our things where we have n observations, so our responses, the y's, our explanatory variables, so in the simple linear regression we would just have one column of explanatory variables, the x's, and our random terms, they can all be thought of as column vectors with n entries, where n is the number of observations. Okay. Now, one useful thing to do if we want a fully vector form formulation of the simple linear regression model is to define one more vector, which I'm going to write as a bold one, or on the blackboard I'll underline it. The subscript n just indicates this is for n dimensions, so this is a very simple vector. Every entry in it is a 1. Okay? So 1n here is a column vector, all of whose entries are 1. So if we define these vectors like this, then we can see that the simple linear regression, so remember the simple linear regression is just yi is beta naught plus beta 1 beta I plus epsilon I, so that's a simple linear regression. We can see that this is just the ith line of the vector equation, that y is beta naught, which is a scalar, times the vector whose entries are all 1, plus beta 1 times the vector x, plus the vector epsilon with the random terms in it. So the linear predictor terms are here, and then the random term epsilon is at the end. So this is a vector equation. The ith element, so the equations you get for the ith elements of each part of this correspond to what we had before. Okay? So saying that this is true for all I is exactly the same thing as saying that this vector equation is true. Okay, so we can actually do something a little bit more sophisticated. So let's now define a matrix which I'm going to call X. And what this matrix is going to do is it's going to combine the information in these two vectors that were in the linear predictor terms. So the one that got multiplied by beta naught and the one that got multiplied by beta 1. So its first column is going to be the ones which came from this vector over here. And its second column is going to be the vector of the x's. So its second column is going to be the lowercase x that we had before. Okay, so that's a vector which we're going to call, that's a matrix which we're going to call X. Now, let's define another vector. So another vector, which I'll call beta. So again, the underlining indicates vectors, and that corresponds to bold in the notes. And this is just going to have the two entries, the simple linear regression, which is two entries, beta naught and beta 1. Okay? So again, it's presented as the transpose of a row vector in the notes. Now, if you consider what happens if you take the matrix X here and then do matrix multiplication with the vector beta. Okay, so then the first row that you get is going to be 1 plus 1 times beta naught, so you get beta naught, and then plus x1 times beta 1. So we get beta naught plus beta 1 x1. And similarly, for the next term we get beta naught plus beta 1 x2, and so on. We end up with beta naught plus beta 1 x n for the last term. Okay, so if we multiply the matrix X by this vector beta, we get this new vector whose terms are beta naught plus beta 1 x1, beta naught plus beta 1 x2, and so on. So in fact, they're exactly the terms that we were getting here, so the linear predictor part of this, without the epsilon r. So that means that we can write our simple linear regression model very simply as the vector equation that y is the vector x beta, which I've just calculated over here, plus the vector of the epsilons, which is this one here, consisting of the random terms. So the x beta here gives you the linear predictor terms, and the epsilon gives you the random terms. Okay. Now, it turns out that we can do this for any model in the sort of family of models that we're thinking about. So for both the models up here, the multiple regression and the quadratic regression, you can write it in this form, y is x beta plus epsilon, for an appropriately chosen matrix x, which is called the design matrix, and a vector of parameters beta. Okay, so I'll do a little bit more about this later on in the lecture, but for now I'll just give you a quick sketch of the quadratic regression. Okay, so we need three parameters here, beta 0, beta 1 and beta 2. So our vector of betas will look like this. It's a column vector whose entries are beta 0, beta 1 and beta 2. And our design matrix X, so before we had two entries on each row, so 1 and x1, but now for the quadratic regression, we're going to want three terms. We're going to want to multiply beta 0 by 1, beta 1 by xi, and beta 2 by xi squared. So in each row, what we're going to want is 1, then x1, then x1 squared in the first row. Here we're going to want 1, x2, x2 squared, x1, x3, x3 squared, and so on. So x is going to look like this in the quadratic regression. Okay, so that's a special case of an example that I'm going to consider in a bit more detail later on in the notes. Okay, so we can indeed express both the multiple regression and the quadratic regression in this form, y is x beta plus epsilon, for suitable choices of x and beta. Okay, so now let's take our general form here. So this is the general form of the linear model. Okay, so y here is a vector. It's a column vector with n entries, one for each observation, and it contains the observed responses. So this contains the dependent variables, y. Okay? X is a matrix, which we've just said is the design matrix. So these are the coefficients that we've got here. So these are the independent variables. These are the variables that we're interested in whether they can explain our data, the explanatory variables. Okay? Note, as in this example, that we may have some functions of the explanatory variables. So here we've really only got one variable for each observation. So for example, x1 for observation 1. But in the design matrix, we have some functions of it. So we have 1, then we have x1 itself, and then we have x1 squared. So you may have more columns, in fact you almost always will have more columns in the design matrix than you actually have explanatory variables. And I'll say a little bit more about the terminology there later on. Okay, so beta is a vector of unknown parameters. There are p unknown parameters, so it's a column vector with p elements. Okay, and typically we'll start with beta 0, which will be the coefficient for the column of 1s. So the last one in the last entry will actually be beta p minus 1 because it's a p-dimensional vector. Okay, and the epsilon, so this is a vector of random variables. These are not observed, and this corresponds to the random part of the model. Okay, so some facts about the way that we think about the model. So firstly, p here, the number of parameters that we're going to try to estimate, which corresponds to the height of this vector and the width of the x matrix. This can be anything we like. So we could have lots of parameters that we want to try to estimate. The only warning here is that you have to think about how many observations you've got. So it certainly doesn't make sense to try and fit more parameters than you have observations. That's never going to work. You also shouldn't be trying to fit the same number of parameters as you have observations. Even a little bit less than the same number of parameters as you have observations, probably the noise in the data will be confusing you and you're getting spurious information if you do that. We'll talk a little bit more about how many parameters it's sensible to include as we go through the course, but it's always worth remembering that this is a potential issue. You do need to think, am I overfitting the data? Am I trying to fit too many parameters for the number of observations? In the multiple regression model, so the first one that I had up on the screen when we started, so here, the number of parameters here is r plus 1. So there's beta 0, and then beta 1 up to beta r. So there are r plus 1 parameters that we're trying to estimate there. In the quadratic regression, there are 3, beta 0, beta 1, and beta 2. So in the quadratic regression model, p is 3. Okay. So the next thing we need to think about is the assumptions that we're going to make on our random terms. Okay. So some of these assumptions are more important than others, and I'll say a little bit about that once I've gone through them all. So we're going to make the assumption that this vector epsilon, which gives us our random terms, has a multivariate normal distribution. So that simply means that all the components of the vector have normal distributions and that they fit together in a suitable way. We're going to assume that the components have zero mean. This makes sense. If the components of this bit have zero mean, then that's telling us that the x beta term is the mean of our observation random variables given by the y's. Okay? So it's telling us that the expected value of the y variables is what we get from x beta. So the linear predictor actually gives us the mean. So that makes sense. We're thinking of the epsilons as being perturbations around the linear predictor. It makes sense to think of perturbations as having mean 0. We're also going to make what's quite a strong assumption, which is that the components of epsilon are independent. So that means that the random part for different observations is independent of the random part for the other observations. So if you're getting a larger value than the model would lead you to expect for one observation, that doesn't tell you anything about whether you should be getting a similar larger value or indeed a smaller value for the random parts for other observations. So the random parts for the different observations are independent. Okay, so that goes together with assuming that we've got a multivariate normal distribution and actually tells us that the components of the epsilon i's are independent, normally distributed random variables with mean 0. So if I tell you that a random variable is normally distributed with mean 0, there's one more thing that I haven't told you about that we're assuming about the distribution, and that is its variance. We're going to assume that all the components, so the random terms, for all these observations, have the same variance. We're certainly not going to assume that we know what this variance is, but we're going to assume that they all have the same variance, and it's sigma squared. Okay, so this assumption is known using the somewhat difficult to pronounce term homoskedasticity. Okay, so homoskedasticity is the assumption that all the random terms in the model have the same variance. And sigma squared here is another unknown parameter. Okay, so we do not assume that we know sigma squared. So we go back to the simple linear regression, just for the purpose of drawing a picture. Okay, so in the simple linear regression, let's say we've got 5x values, which is the same as what I had in the lecture yesterday. Simple linear regression, the linear predictor gives us a straight line. Okay, so the linear predictor is giving us these values, which are the means of our random variables, which give us the observations YR. So these are the means. Now the actual values, the betas, so the actual values of the y's themselves, the observations. So here we need to add on these epsilons, these random terms. So they have mean 0, so they might be a little bit smaller, might be a little bit larger. So we might get something like that, something like those blue points. Now, homoskedasticity says that the variance, so how far the blue points, the actual observations, are from the linear predictor part, just white points, is the same for all observations. So in particular, you don't have a situation where values up here, which have higher values for the linear predictor, also have higher variance. And as we go through the course, we'll see that there are situations where actually it is the case that values where you have higher values of the linear predictor, you tend to get higher values of the variance. And in that case, this assumption of homoskedasticity fails. Okay? When it fails, the term is heteroskedasticity. Okay, so one of the things that we're going to do in this module is we're going to be interested in testing these assumptions. So once we've got some data from a linear model, we can ask the question, well, do these assumptions appear to be supported by the data? Or is there evidence against these assumptions from the data, which is often a better way of thinking about it. And we'll also actually think quite a bit, particularly later on in the module, about how to use some theory, like the theory of linear models, in situations where these assumptions are not satisfied. And with particular focus on the first assumption of a normal distribution, and on the last assumption, the assumption of homoskedasticity. So we'll see how we can work when we do not have those assumptions. Just to point out, of course, the central limit theorem, which says that if you have lots of little effects, you tend to get a normal distribution, means that often it's not that big a problem if the first assumption, the normal one, fails, as long as the other three hold. so some terminology. So we have our X matrix. So there's an example of an X matrix up in the top right of the board over there. Each column of the X matrix defines what we're going to call a regressor variable, which is the independent variables for our model. Okay, so for the linear model that we've defined, we have one response variable, the y's, and then we have p, which remembers the number of columns of the matrix X, regressor variables. And p was 3 for the quadratic case, and it's r plus 1 for the multiple regression. Okay, so this terminology might seem a little bit weird, because certainly in this example, and in pretty much all the other examples, one of the columns consists of ones. So one of our regressor variables is not actually a variable, it's the constant 1. Okay? So we're not going to worry about that. Our use of the phrase regressor variable will include the possibility that the variable is a constant. If it's a constant, it will always be 1. Okay? You also might worry about the fact that the second and third columns look like they're not really different variables. They're certainly not independent of each other if one of them is always the square of the other one. So we're going to try to maintain a difference in terminology here when the explanatory variable, the phrase explanatory variable is going to refer to the actual original variables themselves, so x1 in that example, whereas the term regressor variables will mean all the things that we put in the matrix X. So in the quadratic regression example, we have just a single explanatory variable, the X term, and we have 3 regressor variables, which are 1, the X term, and the X squared. Okay, so that's the example we've got here, quadratic regression. There are 3 regressor variables, constant, xi, xi squared. See, one up right. So 1 regressor variable for each column in the design matrix X. However, there's only really 1 X variable, and the 3 different columns here all give different functions of that X variable. 1, of course, is a very trivial function, but it isn't. You can think of it as a function, so that works. So what I'm going to do is use the phrase explanatory variables for the actual original variables themselves, and the phrase regressor variables for the functions of them, potentially including a constant, which appear in the design matrix X. So in quadratic regression, we have 1 explanatory variable, but 3 regressor variables. In multiple regression, we have r explanatory variables and r plus 1 regressor variables. Okay? And the regressor variables are always going to be functions of the explanatory variables. Okay, so I'm now going to do a slightly more detailed version of the quadratic regression example that I've already done, with the extension to allow more powers in the linear predictor. Okay, so if we think about extending the quadratic regression to have more powers, then we would expect to have a b3 x1 xi cubed term, and for the next power after the quadratic one, and ultimately, if we're going up to a degree r polynomial, we'd have something involving the rth power of xi at the end. So this would be our linear predictor, and then again we have our random term, the epsilon r's. Okay, so y is going to be just as it was before. It's going to be a column vector with the observed values of our response in it. So each observation goes as an element of that column vector y. Now the beta variable, so we want a vector which is going to have the entries beta 0, beta 1 up to beta r in it. So again, this is just a column vector, beta 0, beta 1, down to beta r. And what we want is to get a matrix, design matrix, whose, when we multiply it by beta, the ith row is going to give us the linear predictor bit here. Okay? So what's that going to look like? So we want to get something when multiplied by beta 0, which is going to give us beta 0. So that can just be 1. Something which when multiplied by beta 1 is going to give us beta 1 xi. So in row 1, so that's actually going to be beta 1 x1. So x1 will give us that when we multiply it by beta 1. And then the unwritten, included in the dots in the middle there, term beta 2 x1 squared, we're going to get, if we have beta 2 from here, multiplied by x1 squared there, then x1 cubed, and we continue, and the last term, when multiplied by beta r, should give us beta r times x1 to the r, so we should get x1 to the r. Okay, and similarly for the other variables, so for each variable, each of the original x variables, we get a row of the matrix whose first entry is 1, then the variable itself, then its square, then its cube, and so on up to its r power. Okay? So P here, the number of variables, is r plus 1, because there are r plus 1 coefficients of this polynomial that we're trying to estimate, from beta 0 up to beta r. Okay, so there are p terms that we're trying to investigate. Okay, so at this point, if you're following through in the notes, you'll see that it says task 1. So in the notes, scattered through them, there are some tasks. Mostly these are fairly simple things for you to check for yourself to make sure that you're following through the ideas. So the task that it gives you here is to take the multiple regression model, which was the first one that we had on the board at the beginning of the lecture, and make sure that you realise what the correct form for the matrix X is in that situation. Okay. So let me go back to this picture. I'm going to draw a very similar one. So again, I want to think about simple linear regression. But again, the only reason why I particularly want to think of simple linear regression here is because I can draw it easily on the board. Okay. So we've got some data. So we've got a cloud of points. Something like that. The other one there. And we want to use the data to estimate the model that we're actually using. So we want to estimate the parameters. So in simple linear regression, it would be beta 0 and beta 1. Okay. Now that corresponds, so beta 0 is an intercept, beta 1 is a gradient of a straight line. So this corresponds to drawing a straight line through the data. Okay, so it's going to look something like that. Okay, so that would be our estimate of the model. So that's going to be the line beta 0 hat plus beta 1 hat x. And the hats here are going to refer to the fact that these are estimated values. So we have a model, we don't actually know beta 0 and beta 1. Beta 0 hat and beta 1 hat are going to be our best estimates of beta 0 and beta 1 given the data. So pretty much whenever you see a hat on a parameter in a statistics course, that's what it means. It's the estimate of the parameter in question. Okay, so imagine that we have some estimates of our parameters, our betas. So this could be simple linear regression, but it could be one of the other models in the family as well. So let's assume that we have estimates of p parameters, beta 0 up to beta p minus 1, and they have hats on them, so they're estimates. Okay? Now, we can put those in a vector as well. We can put the estimates of our parameters in a vector, and following that convention, the vector beta hat is the vector whose components are the estimates of the parameters. Okay, so given that we have estimates of the parameters, we now have an estimate of the linear predictor, the non-random part of the model, for each observation. And these are called the fitted values. So I will put on the fitted values, the values of the linear predictor, in this example. So these are going to be blue, okay, and they are the points on the straight line which correspond to the various x values. So for this point, the fitted value will be just above it on the straight line, and similarly for the other points. Okay, so the blue points that I've just marked with crosses on the orange line, those are the fitted values for each of the original white points, which were the data points. Okay, so those are the fitted values. We can also think of them in the linear algebra way. So if we think about the rows of the individual rows of the design matrix X, again, that's just an example of the design matrix for quadratic regression. And we think of that as a row vector. We can multiply a row vector by a column vector. And that gives us a number. And that's xi transpose beta hat. That then gives us the fitted value in that case. Okay? And furthermore, if we take the whole matrix X, that's essentially the same as doing it for every row at the same time, and the matrix product of X, the design matrix, with the vector which contains the estimated parameters, beta hat, that gives a vector as an answer, with n elements in it. Those n elements are the fitted values for every observation. So the matrix product X beta hat gives the fitted values for every observation. Okay. So about the question now of what is a good way of estimating the line, the orange line in this picture, beta 0 hat plus beta 1 hat x, or for a more general linear model, all the parameters beta 0 up to beta p. What's the best way of estimating those parameters given some data? Well, if we have a particular set of estimates, then we get a set of fitted values. Okay? And what would make a good set of fitted values? Okay? Any suggestions? Okay. So what would make a good set of fitted values? Well, if they are typically close to, if they're close to all the points. Okay? So if the fitted values are close, which are the blue points here, are close to the original white data points, then that suggests we have a good set of fitted values. So it's going to make sense to think about the difference between the original data point and the fitted value. Okay, so given observation I, we're going to consider the difference between the observed value, the yi, which is the white cross, and then the fitted value, which is the blue cross. So we want to consider the difference between those 2 points. Okay, so we will formally define it as yi minus the fitted value. So these are known as the residuals. So the difference between the observed value and the fitted value for observation I is the residual for that observation. Okay, now previously we used the Greek letter epsilon for something which was similar, which was the random element in our model. We're now going to use the related Latin letter E for the residuals. So the residuals are the differences between the observed values y and the fitted values x beta hat. So just to emphasize briefly the difference between the e's, the residuals, and the epsilons, which were the random term in error. Epsilon, you didn't have the hats here. Okay? So the epsilons were the actual random terms, assuming a particular choice of beta values. But we don't know the actual choice of beta values, we have estimates of them, and so the e's, the residuals, are essentially the estimates that we get of the random terms given estimates of the parameter values, which are the beta hats. Okay, so residuals actually play quite an important role in this course. They're particularly important when thinking about checking that the assumptions that we made for the linear model theory are actually reasonable. Okay? These residuals are things which we can think of as closely related to the random terms in our model. The random terms in our model we assumed had some properties. Looking at the residuals can give some idea of whether those random terms in the model are, those assumptions we made about the random terms in our model are correct. Okay, so we said that we wanted to have fitted values which were close to the observed values. So we wanted the difference between these white and blue points in my picture to be small. So that corresponds to saying that we want the residuals to be small. So we want choices of the beta hats, our estimates of our parameters, which are going to make the residuals small. Now, we want the residuals all to be small at the same time. It's very unlikely we can make them all 0 or anything like that. So it's a question of trying to get the best fit that we can And one way of doing that is to think about the sum of the squares of the residuals. And there's an argument saying that basically the reason for thinking about the sum of the squares of the residuals is because the linear algebra works out particularly well if we think about trying to make the sum of the squares of the residuals small. We will also see that in the specific case that we've assumed that we have a normal distribution with our independence about random terms and our homoscedasticity assumption, that this actually corresponds to maximum likelihood estimation. So there's another natural reason to think about trying to minimise the sum of the squares of the residuals. So we can write the sum of the squares of the residuals, again using linear algebra, and this works for any vector. If you take the sum of the squares of its elements, that is the same thing as saying that you take the scalar product, the dot product, of the vector with itself. And that is the same thing as the matrix multiplication of the transpose of the vector with itself. So the sum of the squares of the residuals is the matrix product of the transpose of the residual vector with the residual vector itself. So it's E transpose E, where E is the residual vector. The residual vector was also defined as y minus x beta hat, so we can alternatively write y minus x beta hat transpose times y minus x beta hat. So we're just squaring the elements of this vector y minus x beta hat. Okay, so this sum is known as the residual sum of squares. This is the definition of the residual sum of squares.